Hello everyone. The topic for this presentation is flow dynamics in a wavy channel loaded with anisotropic porous material. Let me start by giving a small introduction about myself. I am Manoj Prakash from SVNIT Surat, currently pursuing my 4th year integrated masters in applied mathematics. This project is done under the guidance of Dr. Sukhendu Ghosh, assistant professor at IIT Jodhpur. The problem which I am focusing on to analyze in this presentation is two-dimensional viscous flow in anisotropic porous material bounded by wavy channel. I am considering two cases where the channel are symmetrical and asymmetrical along the central line. Fluid dynamics is an enormous field with numerous day-to-day applications like underground water transportation, oil recovery, mass or heat transport in a fluid motion. My objective is to solve the above problem using perturbation theory. Perturbation theory helps to understand the effect of boundary wall on the flow and its influence on the backflow phenomena. Perturbation theory develops an expression for the desired solution in terms of a formal power series. We can approximate any physical quantity like velocity or pressure in form of a power series with a small parameter epsilon, which acts as an error. If I want to find the solution of any quantity A, then A can be expressed as A naught plus epsilon into A1 plus epsilon square into A2, so on, where A naught is the zeroth order solution of A and A1, A2 are the first and second order solution of A respectively. On further simplification, we can approximate the solution of A as A equals to A naught plus epsilon A1 plus all the higher order terms. Now coming to the geometry of the problem, we have two impermeable boundaries which are located at y is equals to 1 plus a cos 2 pi x by L and the other wall located at y is equals to minus 1 plus a bar cos 2 pi x by L, where a and a bar are the amplitude of the wavy channel and L being the wavelength. If a is equals to minus of a bar, it represents a symmetrical boundary channel, and a is equals to a bar represents a asymmetrical boundary channel as shown in the figures below. The flow between these walls would be governed by Brinkman equation in combination with conservation of mass, where the first equation represents the Brinkman equation, where u star is the superficial velocity vector, p star is the pressure, mu is the viscosity of the fluid, and mu f is the effective viscosity of the porous matrix, and k is the second order permeability tensor. The second equation represents the conservation of mass equation. The boundary conditions for the problem are taken as no slippage on the walls, which implies both the directional velocities u, v are zero on the boundary wall. And second, the total volumetric flow is conserved, which implies the amount of fluid passing through any cross-section of the flow is same. As we can see, both the Brinkman equation and conservation of mass have dimensional variables. We have to non-dimensionalize all the variables to find the solution. After non-dimensionalizing and separating both the velocity variable, we get the below equation. The first equation corresponds to the horizontal velocity, while the second equation corresponds to the vertical velocity, where alpha is equals to 1 by Darcy's number, delta is equals to aspect ratio of the channel, and lambda square is the ratio of horizontal permeability to the vertical permeability. The boundary conditions are written as below. The first two represents the no slippage condition, while the third one represents the total volumetric flow condition. After using perturbation approximation to the quantities like UVP, it results in U naught, V naught, P naught plus delta square U1, V1, P1 plus all the higher order terms. After perturbation approximation, the governing equation will be in zeroth order terms and first order terms, while the higher order terms will be neglected. The zeroth order equation with its corresponding boundary condition are written on the left side, while the first order equations are written on the right side with its corresponding boundary condition. The solution of these two equations yields a solution to the problem. Few of the results are presented on this slide. We can observe that there is a particular value of lambda for which backflow phenomena occurs in symmetrical case, but backflow occurs in all the values of lambda in asymmetrical case. We can also observe that as the value of lambda increases, the density of the backflow phenomena also increases. Thank you.